the second part of this demonstration, which is about the analysis of the FARS data. And we try to find a couple of interesting insights about what are the most important influence factors for a fatality in accidents, but also to find out, well, how likely is that a person being part of an accident is actually dying in this accident. This demonstration will cover some more advanced data preparation methods. We will make a little bit more deep dive into ensemble models. We will also cover some very innovative multi-objective feature selection techniques. We will demonstrate how to take a predictive model and turn this actually into prescriptive analytics by combining this with optimization schemes. And last but not least, give you at least some hints about how to operationalize RapidMiner models by integrating them into other business applications. Okay, let's get started. This is an overview of the data. We collected in total 42 different fields describing the crash itself, like for example, if the driver or the passenger has been ejected, the road condition at the moment of the crash. We describe the people involved, the age, the sex, and others. We describe the month, the hour of the crash, the atmospheric condition. So all this kind of information, in total 42 different fields. And we collected data from 2009 to 2013, resulting in about 250,000 different data rows. All the data was coded. Also the most important column, which was the severity of the injury. Here's the coding for the severity, and one of the most important pre-processing steps is actually to do the decoding, basically transforming all the numbers in the data back into human readable formats. So let's look into RapidMiner, how that can be done. This is the complete pre-processing for a single year of the data set. The way how the FARS data queries work is that you actually have to download every single year on its own. Okay, so let's have a look at the first element here, the decoding. The decoding here is a sub-process consisting of multiple steps. In fact, one step for each column. So let's go inside here. As you can see, for example, here for the first one, airbag deployed. I can go inside again. And here I have some helper data containing the decoding for the different numerical values. Join them to the data set so that actually I can transform the numerical values into the human readable form, and then afterwards I do some type cleaning here. So I can do this for every single column here. If I look at the next one, I see that this is a little bit more complex. In this particular case, I, for example, also do some other deep pre-processing for more specialized values. Here for the alcohol, for example, I say, well, whenever something is wrong with the data, I don't know the test result, let's replace this by blank. And then we define that blank is actually a missing value. So since those can differ for each column, I decided to actually do the pre-processing for each column on its own. So that's really the collection of steps we can see here, which is maybe a little bit more work, but I think it pays off for the quality of the models later on. Afterwards, I do some more additional data pre-processing. Here, for example, I transform some of the numerical values, which are really just zeros and ones, alcohol involvement and speeding, into binary attributes. Then handle additional missing values. I transform the columns for the IDs, for case and person and vehicle, into real ID columns. Remove a couple of old attributes which are no longer necessary now, rename some of the columns, and last but not least, I also calculate a new one, the vehicle age, by just using the crash year, which is part of the data, subtract from that year the vehicle model year, so I get the age of the vehicle, because that might have some influence on the likelihood for fatality as well. So after all those steps, I actually add a branching here. So this branching is actually checking if a variable is set, remove missing, and if this one is not set, well, I'm not doing anything then. But if this variable is set, then I'm also removing missing value. This is an interesting concept. So you can actually define those processes for pre-processing like this one here. And then you can actually define how this process actually is working by using those process context variables here, and then checking for the values of those variables inside of the process. So this all here is the pre-processing for one single year. We cover the years 2009 to 2013. But then also I have a process here for all the years. So in this case, I actually create a loop here. In this case, I just iterate over all the different data sets. And for each data set, I'm actually now checking again if I should remove missing values or not. I have the same context variable here. And then depending on if I should do this or not, I execute the correct process by using, for example, the remove missing variable here. So that allows now, with this loop and this branching here, allows for very complex data pre-processing operations, or even modeling operations actually, where you can build processes with like looping over different data sets, or only doing certain kind of pre-processing in case you want it to be done. So after this loop is finished, the result is going to be the 5 data sets for each year. And then in the next operation, I just append all those years into one large data set. I remove the useless attributes. Those are attributes with constant values in case there are any. I don't think actually eventually there have been any, but just to be on the safe side. And I store the complete data set again with a branch. And the branch here basically defines if, what kind of name I'm using without missing or just the complete data. So here you see another example how this looping and branching can really create very complex processes. So after all those loops here and all the pre-processing have been executed on the server, the result is also stored on the server. In this particular case, I actually copied the data here to my local machine, so just to be a little bit faster and don't need to transfer whatever 50 megabytes of data back and forth. So this is the complete data set, 43 columns. Well, why 43? Didn't we say 42? Well, remember we calculated this one additional column, the vehicle age here, as well as part of our data pre-processing. So that's 250,000, or about 250,000 rows. You can inspect them here now. Probably a better idea is to look into the statistics, just as we did this before. We have a couple of ID columns like those up here. And then all the other information, we also see those typical problems, missing values. For example, for alcohol test result, this one here is missing in well, more than half of all the cases. That's probably not really great. And there are a lot of other missing values, so certainly we need to do something about that. As before, we can have a look into some of those details here. For example, the crash hour. We can immediately see that most of the crashes are happening actually here in the afternoon region. Nothing which is probably a big surprise. People are driving back from work, are a bit tired, and there's a lot of traffic going on at that point in time anyway. So you would expect more accidents here. But those are the typical first insights you can make right away. Vehicle age, also no surprise. Well, they are more younger vehicles than really old ones. Okay, so this is how the pre-processing looks like, how the data looks like. But what I would like to do next is basically shifting to a different part of the RapidMiner platform, the RapidMiner server, and show you also how can you share those insights with other people as part of a web-based interface, which allows you to do some explorations and explanations and share them with others. So you're seeing now the web interface of RapidMiner server. That is a place where you can create interactive web applications completely based on the RapidMiner processes, so again, without any code involved. So by just combining different processes into a new application, you can actually build rather complex apps which you can then share with others. So let me show you one I created for this crash analysis here. So the first thing you see is a little bit more like a BI-like report about those 250,000 people in those years. You see, for example, the distribution between fatal injuries, like about 33%, no injuries, about 25%. You see what we already saw in studio, that indeed between 3 p.m. and 6 p.m. there's a peak for accidents. I picked a couple of other interesting insights here. Indeed, people have more accidents on weekends. So Sunday, Saturday, and Friday are those days with more accidents. One thing I found surprising was that there's actually a peak in the summer month. That's something I didn't expect. I would expect that there are more accidents during the winter, but that indeed is not the case. And then last but not least, we can also answer the very important question, are there more males or more females causing accidents? And indeed, it's much more males. So good that we clarified this one here as well. This is, as I said before, is a more like BI-like report, but the special thing about RapidMiner is that you can combine those elements with other applications. Keep in mind that every single visual element you see here is created by RapidMiner process. So first of all, that means that you can also export this as a web service into other applications. We have connectors to Tableau and Click and practically every BI tool out there. But that also means that you can interact with those visualizations here. So for example, here is the number of accidents by state. There's a lot of accidents in Texas, so let's click there. This now causes the execution of a process delivering the top 10 accidents in Texas. And since a process is executed, we can do whatever you want to do inside of this process. So you can send out an email, you can write the data back into the database, you can purchase some stocks, you can trigger some web services or some actions in general as part of other business applications. So that is really important because this is one of the key ingredients of what we call operationalization. So you're not just getting some predictions, but also you can trigger business actions and connect this to other business applications. But still, again, this is a little bit more BI-like, so let's move on to the next view here, which is the first view with more advanced analytics. This one here is about influence factors. So what is really causing fatality or injury or no injuries in accidents? And you see the most important influence factor is indeed the ejection, and then the restraint system, the speed limit, and so on. So let's have a look into the details. Ejection is very important. Well, you can see it here right away. If you have been ejected out of your car, it's pretty much sure that you're dead. While if you haven't been ejected, then you have a good chance that there's actually no injury as well. The restraint system is also very important, and I found this here very interesting. So first of all, well, if you didn't use any restraint system, well, then you have a very high likelihood for fatality, in fact 70% here. If you use a shoulder and lap belt, it's much safer. So not a big surprise here in the two right columns. This is how you would expect this. But interesting is, for example, for the motorbikes, it doesn't really make a lot of difference if you're not wearing any helmet at all, or if you're wearing a helmet. So that was interesting. Also, the child restraint systems, there is not much of a difference on fatality if it's a rear-facing system or a forward-facing system. But having said this, I still think that there's a higher likelihood for no injury with the rear-facing system, so that might be interesting for you as well. Alcohol test results, also relatively important here. Interesting again, no alcohol, you have a much higher likelihood to survive. And if you really have like 0.2% alcohol, well, this is really a high likelihood for fatality. I think, of course, it's not really the alcohol in your blood per se, it's really more about your behavior which led to the accident, which is probably totally out of control if you're that drunk. Age has a lot of influence on the fatality as well. If you're an elderly person, then it's unfortunately more likely for you to die in the accident compared to a younger person with a higher likelihood to survive. Okay, so this is the first time we have advanced analytics. There's actually more on the next step. Of course, we can have here a decision tree and can see that this decision tree here is actually correct in 76% of all the cases. But actually the best model has been an ensemble method using a Bayesian boosting ensemble and using a naive Bayes as our base learner. So this was delivering an 84.4% accuracy for those three classes, which actually is pretty good. Let's have a look here on the right side. This is one of my favorites. This is actually using a multi-objective optimization scheme for this naive Bayes here to figure out what are the best features to use for the learner. And here on the x-axis you see the number of influence factors, and here you see the accuracy on the y-axis. And that graph here tells you if you're only going with one single factor, then please go with the driver condition. That's going to be a 71% correct model already. But if you have two, then forget about the driver condition. In that case, go with body type and restraint system being correct in 77% of the cases. Then the same 2 plus airbag deployed for 3, the same 3 plus rollover for 4, and so on. So this really is interesting because it shows you like how well can you get actually by adding more data, more influence factors, but it also can, like in this case here between 1 and 2, can show you that this can change to complete different feature set between different feature set sizes, which often is interesting on its own. We have some clustering results here with the prototypes down there, but I think we'd rather move on to what I find the most exciting part of this whole web app, which is really about prescriptive analytics and the operationalization of those prescriptive actions or predictive insights. So in this particular case, what we have been doing here is we allow you to make a couple of settings about yourself, like the age bucket you're in, the sex, if you sometimes drink alcohol before you drive, a typical speed range you're driving at, or weather conditions you're driving in. So after you make those settings here, then we take those settings, we take the predictive model predicting the fatality for all the 250,000 cases we observed, and both together are going into an optimization scheme, figuring out what is the best vehicle make and body type you could buy in order to have the lowest likelihood for fatality. So for those settings up here, the best car you can buy is actually a Dodge as a standard pickup, and still you have a fatality of 90%. So that is really the result of the optimization scheme already. So let's make a couple of changes here. Let's say older person, drinking alcohol, driving much faster, in the rain, so wet streets, let's say in the dark. And if I change those elements here, now RapidMiner is again doing the optimization, going actually through tens of thousands of different possibilities here. And in this case, I'm getting the prescriptive action. Well, in this case, buy please a Honda. And as a large utility car, that's probably the best idea, only having a fatality of 11% in this case. Well, then let's operationalize this and let's just buy a new Honda, which of course in this particular case is a little bit artificial, but you get the idea. I would like to show you two elements or two processes for this. One is for this prescriptive and operationalization here, and the other one is actually for the multi-objective optimization and feature selection we are using down here. So this is the optimization loop using the predictive model and also all those input factors we have defined here in the web app. But of course you can integrate this into other business applications as well. So here's just a little bit of preparation for the optimization loop, and that's happening down here. So now we are going through the potential values, looping through all of them, apply the predictive models for all the different combinations we are trying out as part of our optimization, plus the settings you have defined as a user here, or maybe some process has defined, some outer process. And then we collect actually, or we calculate how well or how large the fatality is predicted. This one then is used here to actually store the current values in fatality, so the current model, vehicle make, and the current body type, together with the fatality, the predicted fatality in case it is lower. And after we went through all the optimization, we then generate basically a data set delivering the prescribed vehicle make, body type, and fatality, which is then displayed to the user or used in other applications. And last but not least, I would like to show the process for the multi-objective feature selection. We are using an evolutionary algorithm for this one here, with all the settings you can see here on the right side. Well, let's focus on the key settings here, the population size of 12 and 40 generations in total. So let's execute this process here and you will see what's happening in a second. Okay, and now what we get here is a so-called Pareto front. So here, in this case, it's on the x-axis the accuracy. For the report, I actually shifted this over. And here's the number of attributes on the y-axis as a negative because it's better to have only few attributes. So, and you can see how this evolutionary algorithm now is actually finding the Pareto front of the best solutions. So this is what we get here. So now it's stable, so the optimization stops. But what we can see is exactly the information we have seen before. So if you only go with one attribute, well, go with the driver condition, etc. And you as a user can inspect this now and then just select the preferred data set. Let's go maybe with this one here. And this one then is delivered to the user or stored in the repository like we are doing this right now. Well, and that is the result. Thank you for joining me in this RapidMiner demonstration today, and I hope that you enjoyed it. I also hope that you saw that RapidMiner is truly a full platform for effortless predictive analytics. That means that there's never any coding required, but of course you can add your own scripts if you want to. We have the enablement of analysts through our wisdom of the crowds, giving you the best recommendations for optimal data preparation and modeling. And of course, we also have those reusable building blocks, which further speed your work up. In fact, we see a performance boost often of 50 times and more because of the very advanced data preparation and reusable building blocks, wisdom of crowds, and an overall this visual paradigm. RapidMiner is also a very powerful platform. Think about the data preparation and combine this with loops and branches as we did in this demonstration here. Combine this with your own R and Python scripts, for example. And even better, you can push down all those computation into Hadoop clusters. And since the latest release, that's even true for R and Python scripts, which can also be pushed down into Spark. And we discussed the operationalization of models. I think that is very, very important because a predictive model alone just gives you insight, but you need to close the loop to prescriptive action. And that's really what we did here. We use a predictive model, combine this with optimization schemes, and figure out what is your best course of action, and then you can use one of the more than 500 connectors to business applications to automatically trigger the execution of this action from RapidMiner. We discussed the interactive web apps and that you can also take those individual results and integrate them into other systems as well. Thanks for watching.